Welcome, everybody. This is the Impossible Metals monthly webinar for the month of April 2024, and I'm super excited to introduce Dr. Wolfgang Bernhart. Wolfgang is an absolute expert on lithium-ion batteries, the market, the technology, the automotive industry. I've been fortunate to listen to a number of his presentations at very key events like the Battery Show and others, and I think it's going to be really insightful. So thank you very much, Wolfgang, for participating, and over to you.
Thank you very much, Oliver, for the invite, and I'm happy to share a little bit our perspective, my perspective on the market and technology. My name, as already been said, is Wolfgang Bernhart. I'm a senior partner at Roland Berger. I run our Advanced Technology Center in Automotive and Industrials on a global scale, and a significant part of that is our work around lithium-ion batteries. We have worked in the last couple of years in quite a lot of projects with major OEMs, but not only in the car and truck side, but also with companies in stationary, in other applications, with module and pack integrators, with quite a few of the largest and globally active cell manufacturers, equipment manufacturers, materials companies, miners, refiners, and governmental organizations, also in the US, but also in Europe, on growth entry strategies, supply chain strategies, partnerships, due diligence work, market technology studies, but also operations and cost reductions like cell manufacturing task forces, ramp-up support, or reduction of battery and cell costs. So today, I want to give you an outlook on the lithium-sodium-ion battery market and technology trends. I will talk about the battery market. That is quite in a flux. So the figures I will show are based on our last forecast from Q4 2023. That one will probably change a little bit for the next few years, given the situation in the markets in the US and in Europe. We expect a slightly slower growth than what I show you, but you are happy to contact me to get the latest figures in probably 1-2 weeks from now, and the implications. In general, we see an unbroken trend towards electric vehicles, even if the adoption might be a little bit slower than what has been expected, for example, a year ago. I will then go a little bit in cell technology trends, talk about how we see the market development, what we see on the cathode side and on the anode side. And last but not least, talk about pack trends, specifically what we see in China, and the implications also in the West, where everybody is now rethinking and going more towards cell-to-pack and cell-to-chassis technologies. So these are the three areas. I suggest we collect questions in the chat, and I will keep enough time for discussion to make this interactive and not only a seminar. Yeah? I think we are not a too big group to allow for discussion here as well. So let me start with the market. And as I said, this is based on our Q4 assumptions and our Q4 forecast, which takes into account the current legislation. And that's important because there's a lot of discussion around current legislations, both in the US and in Europe. There's a lot of uncertainties given the fact that we do have elections in North America, in the United States. We do have elections to the European Parliament also in fall this year. We do have elections in India, and those elections might change some of the legislations in Europe. For example, there's the ICE ban that's assumed here, so that no internal combustion engines vehicles that do not use completely renewable energy might be sold after 2035. That could change a little bit. That could be postponed out a little bit because of some political influence of the EPP, the European People's Party, that wants to move that ICE ban out or even cancel it. I don't think that will happen, but a small change can happen, and the same is true for the CO2 emission targets for 2030. The next year's emission target will not change, but everybody is already there more or less. And also in the US, the subject of EVs became quite politicized, so there might be also some implications in the 2030 timeframe. Nevertheless, we do see an unbroken long-term trends towards EVs. That is the main driver for demand for electric vehicles, at least until 2035. After that, a lot is also happening, or more driven than probably a bigger impact from stationary storage systems. What we have here is also lithium and natrium-ion, sodium-ion batteries. In the 2032 2030 timeframe, we do see roughly 4.5 terawatt hours in lithium-ion batteries and up to 500 gigawatt hours in sodium-ion. Again, that share can change a little bit depending on the price of raw materials, specifically lithium. The higher the lithium prices, the more attractive sodium-ion gets. But with current prices, sodium-ion, at least in the chemistries that we do have in China, or that we do see in China, is not economically not more attractive than lithium-ion batteries. As I said, underlying figures based on for passenger cars, based on the S&P Global Mobility forecast. A new one will come out later this month. Probably still very bullish, I would say. We will come up with a slightly revised forecast that could be more in the 2030 timeframe, 5% triggers lower on the BEV side, but it still means that the overall forecast coming from 1,500 roughly plus minus gigawatt hour this year will still triple or roughly triple until 2030. So a significant increase in batteries. But as I said, there's a high uncertainty with respect to the elections. What will happen on the Inflation Reduction Act? There's also a clear push, and that might be even more pushy, to exclude Chinese supply or to exclude Chinese companies from being active in the US. After the elections, we do have the new Green Deal, but maybe some questions on the timing of the sales ban, as already mentioned. And again, also in China, possibility for restrictions. So uncertainties are there, and that has to be kept in mind. And it also impacts the raw material supply chains, or the whole supply chain of battery. It impacts material price expectations, the demand and supply of materials, and investments in new projects. That can have an impact also on the availability of material, while we don't see a bottleneck of raw materials in the next 5-6 years. It could mean that projects are being postponed, and it definitely increases uncertainty. There's a topic of the specific chemistry demand, and I will come to that also, that impacts here a slowdown in EV sales in China, in Europe, in North America, but specifically in Germany. That can have an impact. Alternative chemistries, advanced LFP or LMFP, again, I talk about that, will impact the supply chain. New mining technology, as like deep sea mining, as done by Impossible Metals, might impact the supply side, and politics. So uncertainties are all over in the supply chain, and therefore, even if I presented very specific figures, I think the advice here is think in scenarios and have those uncertainties in mind when implementing your strategy. Focus on the no regret moves, and make the decisions in time, but also not too early, and implement flexible and stable supply relationships, supply chains, and concepts. That's very important if you talk about the market and the uncertainties here. But at the same time, we also see that not only politics are uncertain, or also, and this is still figures from last year, now going down again in Europe, while the longer term trend goes upwards, there's a lot of fluctuations, and everybody who's talking about lower figures, it always depends what you use as a base case, as you can see from these very volatile sales figures in the different markets. For specifically for Europe, maybe less for North America, but for Europe, what also triggers uncertainty, and what also triggers a clear trend to looking more at costs in batteries, in battery cells, and in battery packs than in any other KPIs when we talk about innovation, is the portfolio of Chinese OEMs that comes with a significant price advantage compared to European and US players. The Chinese companies here, and we just put it a list price here, in that case in euro, but divide by 1.1, and then you have similar figures. In the US, there are not that many Chinese cars, but in Europe there are. You can see that Chinese cars are typically significantly more or lower priced. You can get them for even 20,000 euros already in Europe, and they are priced even with higher driving ranges. So there is currently no offering for affordable entry electric vehicles in the European market below 20,000 euros, and also no real affordable electric vehicle in the US. That might change with the new Tesla model, but that's really a big point. And achieving cost parity with combustion engine is therefore crucial for further growth in BEV sales. And in order to achieve those figures forecasted, and it doesn't matter whether it's 50-something% or 60 or 40% on a global scale in 2030, prices need to come down. Prices are heavily dependent also of raw material costs. Typically you have the battery is between 30 and 40% of the vehicle bill of material or of the vehicle material costs. So it's very important, the raw material prices. They have gone down significantly. We do see them flat. I don't show a figure here, but we do see them more or less flat for the time being, and then increasing again in the 2030 timeframe, which would have a 10% impact roughly on battery cell costs if you talk about NCM material, but not more. So the very high prices that we have seen last year are probably an exemption. But nevertheless, there could be still very high fluctuations in prices in the next couple of years, and that are topics that will also create uncertainties, and those high price volatility and price fluctuations also impact the business cases of the OEMs. A lot of OEMs make up their business case at a certain cost level, and the volatility of the prices, even if OEMs now hedge raw material costs also for lithium and other critical minerals, that is seen as something negative in the overall business case and in the finance and controlling departments of the OEMs. So that is why they are also reviewing their strategies, most of the OEMs planning with lower BEV sales than what they have planned a year before, and most likely higher hybrid and plug-in hybrid sales than planned before. But again, we do see the market growing. We do see it. There is no turnaround. We see a clear trend towards BEVs and a clear trend towards the need for investments in the industry. That's also fueled by the technology trends. We have now already a quite extensive portfolio of technologies on the cathode and the anode side. A lot of discussions around the emergence of solid state technologies. I come to that in a minute when I talk about the anode side. We do see solid state coming to the market, but we don't see it as a significant share. It's probably more in the share of a lower one-digit percentage range in the 2030 timeframe. For automotive, there might be specific applications in aerospace and defense, for example, where there will be higher shares that take advantage of the higher volumetric and specifically gravimetric energy density. There are a couple of other technologies that gained increasingly importance. Everybody was talking about high nickel shares. I will come to that in a minute. We do see that as well, but we will probably also revise our forecasts here and more towards a higher share of LMFP and LMFP and NMC blends. So lithium iron phosphate and manganese, either pure or with a certain NMC content. These are technologies that are already brought to the Chinese markets. CATL is selling LMFP under the M3P name. So if you have watched the announcements of CATL and even what they have shown in recent trade fairs, that's LMFP that's already in the market and is expected to come to and be produced also in Europe, but in 2-3 years from now. Then there's LFP as a cost-effective cell chemistry with lower energy density, but significantly lower cost, and that will be adopted and will see a significantly higher share in the market than what has probably most of the analysts have thought of 2 years ago. We do see that mainly coming from China, and that's the reason why companies like GM or Ford are going into technology licensing agreements and service agreements to run LFP cell plants in the US as well, in order to have affordable offers for the volume vehicles. And then we do have typically with hard carbon anodes and liquid electrolytes, the sodium-ion batteries. They are only relevant for the entry segments when we talk about automotive, but they might be relevant for stationary. Today, mostly Prussian blue cathodes, so cathode material, layered oxide cathodes, cathode materials that is similar to NMC to a certain extent, and therefore also being produced by the same set of cathode material manufacturers in China already. And everything that's on the market right now is layered oxide. The real advantage would come from a cost perspective with Prussian blue, but here there's still a way to go in terms of sufficient high energy densities. So if we compare the different prioritized cathode chemistries that are relevant for the automotive market, then it's mainly nickel rich for the premium cars with the highest energy density, also high C rates, some cost reduction potential, but if you look at that as a baseline, significantly above other chemistries. However, we do see 30-40% of the market, and we come to that also in the midterm, being nickel-rich materials. And the potential might be again higher if it's possible to reduce the costs of nickel and cobalt specifically. Manganese rich being offered by companies like BASF or Umicore, and they announced it for quite some time, can be an attractive or can be a solution also for volume cars and for premium cars, with a lower nickel share but a higher manganese share, which gives them a cost advantage of up to 10%. Then LMFP as a good in between, I would say, material with even still a high energy density on cell level. All that's here shown on cell level, high C rates, and even higher cost reduction potential for volume cars. This advantage currently only offered by CATL. Gotion will be the next big player that's bringing it, BYD as well, but outside China, hard to get still. And then LFP with the highest adoption rates, and because of the high safety or the very high safety or intrinsic safety that you see there, offering a good solution to go for cell to pack or cell to chassis solutions that can then lower the gap in terms of energy density on the system level, and also lower the gap, even increase the gap or increase the advantage from a cost perspective on the system level because of the higher functional integration. And sodium-ion, as I said, because of the lower energy density, mainly for entry cars in China or maybe in India, Southeast Asia, definitely not in Europe for the time being, or in the US for the time being. And something that will have a certain share, but will not really kick out lithium-ion batteries out of the market. So that's what we see on the cathode side. So kind of switch, and I show here again our figures from last fall. We will change that, and I indicate that with the forecast trends on the right side. So we expect a higher share of LFP, LMFP, probably in the 45% range, but significantly higher than what's shown here. We expect for the high nickel NMCA type of materials a slower share than shown here, so probably less than 28%, more in the 20-25% range. Also for NMC, we do see a slower share. We might see a higher share for NMC 622, specifically the new developments that allow for higher voltage window, and therefore for higher energy density than what we have seen in the past. And manganese rich probably more in the same range or slightly lower because of the slow developments that we see in technology development. So the general picture will remain the same. The blue is the bluish is the nickel-based ternary chemistry. We see them still being the majority in the 2030 timeframe, but the LFP, LMFP getting a little bit larger share. To what extent that is happening in North America is really depending on the availability to build a local supply chain. We have the first non-Chinese company that will manufacture LFP cathode material in North America. They have already announced that. We do see the respective production in Europe as well, but it really depends, the adoption rate, also on the build-up of local supply chains for that material. That's one side of the equation. But the energy density, if we move back to here, is not only impacted by the cathode side, but maybe even more by the anode side, because that's the current bottleneck. And here we basically and apologies for the a little bit crowded slide, and I will not go through everything and all the details, but what we do see actually is from graphite that we have currently mainly and also in mass production with a specific capacity in milliampere hours per gram of 330 to 360, 365. An increase of that capacity with either low silicon graphite blends that are sometimes done already. We characterize that as 5 to 20% silicon share. That would significantly increase up to double the specific capacity, and therefore increase the energy, the volumetric energy of the cell significantly. That has an impact on manufacturing costs, obviously, but also on the overall system costs. Two silicon dominant blends that we mainly will see in the high-end premium markets with higher 50% or much than 50% silicon share. That is something that is in advanced development started and the most promising technology for improving the energy density and fast charging capabilities. So that's something that will come to the market in the next few years and will also have the potential to reduce costs, to blend graphite with silicon technologies. And there are still some technical challenges, but we expect that to happen pretty soon and have a significant impact on the cost side, or as potentially a significant impact on the cost side, but also on energy density and fast charging. Lithium or anode less, so basically no anode active materials or lithium metal anodes is in development. We do see, if we say no major market launch, then we mean we expect roughly 100, maybe 150 gigawatt hours of capacity until 2030 out of the 4.5 to 5,000 gigawatt hours. So a lower percentage point, single-digit percentage point that will mainly be used in higher-end electric vehicles. But depending on the approach, it also can have a cost impact. But that needs to tackle down then to the whole industry and supply chain. Typically here, the polymer-based approaches are probably the ones that are more likely, and the oxide-based approaches when it comes to the electrolyte. Still in early stage compared to silicon, and but with some promising approaches from certain players. If you look at a little bit deeper on silicium anode technologies, and there are basically three different types: silicon oxides that are already in use, in serious production for EVs and in consumer electronics, typically a drop-in solution, but restricted potential for cost reduction because of the limited improvement of energy density, and the swelling also limits the silicon contents in the approaches here. Silicon carbon composites, so basically a carbon scaffold structure, that has a high suitability for mass market due to the technical alignment with the automotive needs. There's a cost reduction potential at the cell level due to this substantial improvement in energy density, and the carbon matrix or scaffold prevents volume expansion of the anode. So that's a real interesting approach. There are a couple of companies like Group 14, Sila, 1D that are working on that with different foci, but that is something that will most likely come to automotive and these type of technologies. There are others that are more suited for specialized applications like VT or oil or military use, but typically no drop-in solutions and difficulties in scaling. So really the ones in the middle are that we see coming to the market most early and impacting the market in order to get to those parity with the ICE that is needed to really get to more than 50% market penetration of battery electric vehicles. So much for the anode and the cathode and the electrolyte side of technology, but that's not the only one that's important. It's also the trends in cell integration in getting to higher energy density on the system level and to lower costs. So leading Chinese LFP suppliers offer already system solutions that compensate for lower energy density to cell to pack, shown in the middle, or cell to cell to chassis design shown on the right side. Those with LFP and cell to pack, where you have a direct integration of large cells into the battery pack, and the mechanical stability by pack provided by the pack and the cells, with cells that be kind of intrinsically safe, that allows to increase the energy density to higher levels, which make them suitable also for the mid segment. And we do see European and North American OEMs expect those designs, particularly to enable affordable entry mobility. So that's something we clearly do see in the market. It's already in the roadmap of most of the OEMs when we talk about LFP or LMFP, and something that will see a higher adoption in the market. There are solutions now also to make these cell-to-pack designs serviceable or recyclable. There are new materials that, where, for example, you can reverse the gluing effects by using electrical current to allow for recycling of the cells and not having the need to put in the complete pack in a shredder, which is hardly possible today, or in a big pyro facility, which doesn't make a lot of sense. So we expect the technology to be available to really move the industry away from the module designs more to cell to pack in the next couple of years. As I said, that's already being done. If we also look at that capabilities, it increases not only the energy density shown on the y-axis, but also the fast charging capabilities, because of specific concepts when it comes to the question how to wire the cells, etc. And here again, CATL with the Kilian platform, probably the leader, but and other Chinese already advanced from fast charging capabilities, but we also see it with other players, even European or US players. Nevertheless, with the exception of Tesla, the European and American OEMs are several years behind China in terms of C2P and C2C and cell-to-chassis concept. We had the cell-to-pack platforms already 4 years ago with BYD. SAIC and MG had cell-to-chassis already in 2022, and Zeekr already last year. Cell-to-chassis concepts have been introduced first by XPeng and other Chinese players already before, and only now the new players or the European and North American players are coming up with cell-to-pack concepts, but still no cell-to-chassis concepts announced. So here the Western industry needs to work much faster, I would say, in order to catch up with the Chinese players. The advantage they might have in China is that a lot of the Chinese companies should use those concepts and design their vehicles more or less around the big blade cells instead of requiring specific designs, which makes them faster and also from an engineering cost perspective cheaper. So how do those concepts look like? They are characterized by highly integrated and simplistic pack designs with high material and production cost benefits to be expected. The Kilian platform, cell-to-pack 3.0, has a very simple pack design without cross-bracing. The cooling system takes over again also structural and circular functions and avoids for thermal propagation. And the energy density in watt-hours per kilogram is very high, and it also has a very good fast charging capability. The 3.0 E platform of BYD also means the pack is directly integrated into the car chassis, and the housing of the plate battery serves as a structural element, again here with a very high energy density for LFP. Fast charging capability is not that good, but still not too bad. And then for Gotion, their platform called Astro-Inno, it's a simple cell-to-pack design with 4 stacks of prismatic battery cells and a bottom cooling plate, with even again the highest energy density for LMFP-based materials and very good charging capability. So something that's really interesting and providing, as you can see, close to NMC energy densities on a pack level. And then Asphalt with their Dragon Armor platform, that's model-free double-row integration of plate-like battery cells directly into the pack housings, also with a very short fast charging capability. So that's how competition looks like and the benchmark looks like for what Western OEMs need to achieve. Yeah, I skipped that one because it's going in the same direction. It just shows the steady development from a relatively low volumetric pack efficiency. So if you look at the total cell volume to the total pack volume from 55% to over 70%, that's significant, and that has an impact on costs, on energy density, obviously, and other KPIs. Yeah. And then last but not least, if you look at the Skylin pack, that is, if you look in detail, there's no real significant improvement in any certain small area, but the combination of all the incremental improvements that makes that thing so appealing, and that for the Chinese customers, and that gives the real advantage here. Yeah, with that, I would be at an end of my presentation, and would more come to hopefully a little bit of discussion. We can skip back in what I've shown, and I've seen that 1 or 2 typos. So Ollie, I will send you over the presentation with those typos being corrected, and then you can send it out to the participants that are interested also. But it will be shown as it is in the YouTube video, I think.
Yeah. So thank you very much, Wolfgang. We'll hand over to Holly to do the logistics. I would just ask you, Wolfgang, reframe your camera, please. That's you were sliding off the screen.
Oh, sorry. Sorry about that.
Holly, do you want to? Are there questions in the chat?
Yes, we have one question in the chat, and if you'd like to ask Wolfgang a question, if you look down at the bottom of your screen near the center, you'll see a raised hand, and go ahead and click on that, and I will call on you in order. There, exactly. Wolfgang did it.
That was me.
Okay, so and Wolfgang, I'll just read the questions in the chat. I'll add to you. So from Marcel to the SI anode slide, what advantages or disadvantages do you see in the solution from Tesla showed at their battery tech day?
Oh, I would say they go there. Now I don't know which you mean exactly, to be honest, but what I see, the advantage is obviously they already go to these cell-to-pack technologies. They use quite a lot of chemistries. They already use in China, to my understanding, or will use LMFP pretty soon. So there are lots of good advancements, but I would say one of the biggest benefits, or one of the biggest, the best things they do, is to really look holistically across pack, cell, chemistry, so the cell chemistry and the supply chain, where to optimize costs along everything, from a system integration perspective in the car, how the overall battery pack then looks like, what type of cell they use, how the cell is being designed, how the chemistry looks like, etc. That's for me the biggest advantage here.
Okay, excuse me, from Shri. Integrated battery means cars become redundant after its battery life, like mobile phones.
No, I wouldn't. I would not see that. In Europe, for example, you have the battery regulation and the requirement basically to be able to recycle batteries. So obviously the cell to chassis concept here, you have to have a solution for serviceability, but at the same time, most of the problems are rather on the electronic side or on the BMS side. So if the design is done in a good way, you can still do repair here. Second point is actually the lifetime of the cells. Now that's the balance between not over-engineer, but at the same time keep the pack on a certain level of state of charge for longer than 8 or 10 years, for maybe 12, 15 years. That is, I think, something that has been done. And then with the solutions that allow, for example, for reversing the gluing of for example cells, or for reversing or being able to get the cells out of the pack, it also means recyclability. But that's also the biggest question mark that some of the European players make on cell to pack and cell to chassis technologies. What about serviceability and recyclability? Then there was a hand raise, but maybe I quickly answer the question of sustainable supply chains in Europe, and where there is enough feedstock for all the batteries. What I would say, if we look at let me start in Europe and North America. That was the question. In Europe, it's probably not that big an issue, because there is the Critical Raw Materials Act, but at least from a mining perspective, even with permits issues, etc., at least when it comes to lithium and to cathode materials in general, it should be possible. With a higher LFP share, the LFP supply chain is not really locally built up, and most of the refining capacity is around lithium hydroxide in Europe, which is kind of an outcome of the preference 2 years ago, still 2 years ago, of most of the OEMs to go to NCM materials. So that's a challenge. In North America, it's definitely a challenge. That means here to really get everything IRA compliant will not be an easy task. Also, if you just look at NCM materials or nickel coming out of Indonesia as the main source, there are discussions to make that a critical raw materials agreement country, but you still have the issue that most of the mines are Chinese controlled and fall under the foreign entity of concern topic. So it's more the question here of compliance with IRA regulations. But then lithium sulfur, I come to that in a minute, Joseph. Let me answer the other questions. Cathode perspective. There are the announcements in North America on building cathode materials plants, Umicore, LG, EcoPro, POSCO potentially, and some others. Cost competitiveness with China is hard to achieve, but we talk at the same time, we talk about processing costs that are in the low range double-digit dollar figures per kilogram, or in the figure of $7 to $10, and even less now for NCM materials. That is less in China, but at the same time, if you import from China, you might have tariffs, etc., that apply to the complete value of the cathode or prechem materials, and then it's a different story. But capex in China is 50% or less. So there's a significant capex advantage. There's a significant OpEx advantage because of labor safety, environmental safety standards that will keep it always more or less expensive, lower construction costs that make up a significant share. So cost competitiveness with China, also given the significant overcapacities that will be built up, is tough. So pricing, and here the US will see higher prices because of trade barriers, etc., than Europe. In Europe, it's very hard. It's very hard to mention that. And the buildup of gigafactories in the EU, specifically in the EU, will be challenged because of these overcapacities. Announced capacities on a global scale in 2030 are around 9 terawatt hours. So 80% above what we see as even an optimistic demand for 2030. It's already significant higher, and what's being built in or announced in China is more than what's needed globally. So that will mean tremendous price pressure in Europe and some countries that do not protect themselves against maybe even subsidized prices or prices that are not really built on a level playing field. Now, I don't want to let you wait longer, Joseph, on lithium sulfur. It's not. I didn't mention it explicitly, but there are interesting developments, specifically in the US, that might be able to be adapted to major markets. We don't see it in the 2030 time frame significant, but there's a possibility that this technology gains a certain share in after 2030, in the 2035 time frame, specifically from the Texanic company. I don't want to mention too many company names here, but there are some interesting developments, and it's definitely something for niche applications first, but maybe also for the automotive market from a longer term perspective.
All right, we had another question from Marcel.
Yeah, I think I already covered it, but at least didn't cover the second part, the affected build-up of gigafactories in the US. I don't think this affects the build-up of gigafactories in the US because of the IRA and because of probably even higher trade barriers and in general the decoupling or de-risking, however you call it, from probably more decoupling from a US perspective with China, from a European perspective, de-risking. It will affect the business case, and this is why I also said, for example, in Europe, subsidies are needed for newly built gigafactories because the prices of the Chinese and the costs, because they are already more advanced in terms of achieving low scrap rates and high OEE, is so large that you have to have some sort of subsidy to cross the death valley, I would say, the first couple of years until even with moderate import tariffs, local production can be cost competitive. As I said, in the US, imports, I would expect import tariffs are relatively high already. and that takes away a significant share of the advantages they have. Oliver, you have also a question.
Yeah, thank you for the great presentation. But my question is a political question. And, if Trump wins the next administration, what then happens to the licensing of Chinese LFP? Because right now we know Tesla, Ford are building factories with CATL equipment, they're licensing it. They may change the foreign entry of concern. Do you think that loophole will get closed, or do you think things will continue?
That is a very good, but also a very speculative question, I would say. In general, there are. Sorry, I did forget the name of the senators or the Republican politicians that already mentioned that the loophole that if there's a dependency on technology, then this should be also closed.
No,
it was not only mentioned; it was also others that were mentioned was against that subsidization of the basically of the royalties that the companies have to pay in order to use the technology. On the other hand, to be honest, one depends on the technology, and developing that technology from scratch, I don't think is possible. And then the real question is, you could say, okay, I close that gap, and that leads to the situation that maybe there's not an offer of affordable EVs in North America, which then might play in other agendas, political agendas. But that's all speculation now.
Yeah, and if people forgive me, I'll ask another one in a few minutes we have left. And to me, it's really interesting, the LMFP versus the high nickel. And if you factor in current cost and also recycle value, where are they today?
Yeah, I would say the current cost. There's always, I have to say, there's always a cost advantage, at least, or even with significant drops. There will be a cost advantage of LFP and LMFP if it's being produced in China. And that is also driven by the fact that there are specific production routes that use titanium dioxide as a byproduct, also in order to subsidize the costs of the iron phosphate. That might.
I think being manufactured in China, of course, but that would not qualify for IRA.
No, that would not qualify for IRA. So and without if you are an IRA or subsidized NMC, would definitely be cheaper than imported LFP.
Right.
So that means importing LFP is not an option, and this is why those OEMs trying to license the technology. So LMFP is basically what we see in China is a blend with a certain share of NMC. Yeah, that gives you some advantages. Technology Chinese. Yeah. So from that perspective, tough. It's from my perspective absolutely clear that we do see a certain share of or that LFP and LMFP has a significant share of the overall market in the 2030 timeframe, but at the same time, we don't see, as some people say, it's all LFP in the future, all LMFP. That will not be the case. Yeah, you have to have certain energy density for certain types of vehicles. You have people that are less that with the cost difference that is significant, but is at the same time not in a $80,000 or $100,000 car or $60,000 car. It's not so significant than in a $30,000 car. In a $30,000 car, that will be LFP. I have no doubts, because it's simply a solution where the $2,000-3,000 cost difference matters. But for people that want to have a high range, NMC is still the product to go. And there are cell-to-pack solutions being developed for NMC as well. Yeah, that's being done by, and it has been shown by all the three, I think by all the three Korean players at the Interbattery a few weeks ago in Korea. And therefore, this cell-to-pack advantage of LFP is an advantage today, but that gap closes again in the future with NMC going in that direction. Specifically, then the less critical ones, maybe not 95.5 or NMCA, but 62811.
Yeah, well, I think we need to wrap, but fortunately I'll get the final word. So I'll just say one thing. At Impossible Metals, we are attempting to drastically lower the cost of nickel and cobalt, and we believe with our technology, with the deep sea minerals, that could well be possible, because all commodities ultimately are driven by the supply curve in the longer term. And if we can unlock massive supply at a lower cost, and still make decent money, I'm very happy to lower the costs of nickel and cobalt. As a founder of this company, of course, I want to maximize shareholder value, but we are a B Corp. So we also have a public benefit of making available sustainable metals to accelerate the EV adoption. So we have a legal obligation to do both. And so I am very comfortable to make less money, but to enable every American, every European to afford an EV with the best energy density. And so we are trying extremely hard to make a nickel-rich cell cheaper than LFP. Clearly, we have a lot of work to do, but if we could lower the costs drastically, and the other thing is the recycle value of nickel-rich is going to be higher because of the nickel and the cobalt. That's clear. And so if you factor that in, the lifetime, which would be 20 plus years, I believe you could make the argument that nickel is already cheaper because you have that residual end of life value.
The value of and specifically, and we have done that analysis for Europe, but the US figures will be similar, because of the fact that that there's not enough LFP packs and cells available for the next 10-15 years. Most of the recycling operations will be operations that are able to process, and I'm talking now specifically about Europe, where you have that obligation, both LFP and NMC. But that means that the price that an OEM can pay for a pack, or somebody can pay for a pack and make money out of it, is also significant lower. And there is a way, or you could put it the other way around. You can make a margin on recycling NMC packs, but it's very hard to make a margin on recycling LFP packs. Now, that's a big issue here. Yeah.
Yep. Well, I want to thank you again, Wolfgang. This was a wonderful presentation. I think lots of great data, really insightful, and thank you very much. And we'll be announcing next month's webinar soon. I want to thank everybody for joining, and as always, we will publish this on our YouTube channel next week.